Hi, thanks for joining me today. I have a very special guest on the channel. I have Dev, who is an economics graduate from the University of Cambridge. He's going to be joining me today, and we're going to be doing a mock interview. So I'm going to be giving him some interesting maths problems to solve. So hopefully you're feeling ready for this, Dev.
Yes, I'm very excited. Thank you for having me.
That's okay. How long ago was it since I guess you've thought about your interviews at Cambridge? I guess was it something that you kind of maybe pushed away, didn't you kind of want to forget about, or whether was it a good experience?
So I did my interviews online during like December time 2020, so the first of the
Mhm.
pandemic. And I had two interviews. I interviewed at Magdalen College, and that's where I attended. My first interview was pretty not ideal, so um I don't think about that too much. But the second one was a bit better. That was a nice experience. But generally, I don't think about it too much. I've mainly
Okay.
forgotten about the details. But at the time, I remember after the interviews and before I got the email or like the feedback from Cambridge about the offer, I used to think about it every single day. And that was like a pretty stressful time. But I think that's with most applicants.
Yeah, absolutely. The weird period between December the 10th and January the 10th, which obviously includes Christmas and New Year's, a very weird, stressful period. But it is a very satisfying feeling at the end when you do get the offer. Awesome, cool. So for those of you watching at home, what we're going to be doing is I'm going to be opening up a Zoom whiteboard in just a second. I'm going to be asking Dev two maths questions. So a standard interview, a maths interview at Oxford is 30 minutes long, normally on a platform like Zoom, and it will be normally two interviewers in the call, just me today. And one interviewer will ask the first question, lasting approximately 15 minutes, and then they'll swap over after 15 minutes, and the other one will ask a totally different question. So we're gonna dive right in. So
Open it.
uh, just
Also,
open.
just to note, this will be useful for like economics applicants, engineering, NatSci,
Yeah,
physics, ComSci, because their interviews are also quite mathematical.
yeah, absolutely. Yeah, very good point. Yeah, so obviously this I'm delivering this as a math student who did the maths interviews. But obviously, as Dev mentioned, this is applicable. So in fact, I kind of tailored this towards Dev being an economics student, so I haven't put too much certain topics which would only really occur in a maths interview. So absolutely applicable to almost any kind of STEM subject. Um, cool. So if you're ready, we can dive right in. Do you have any questions before we get going?
No, no, I'm excited.
Okay, no worries. Whilst we do the interview, I'll just be scribbling down some notes. Don't worry about that. That's what would be happening in the real interview. And then at the end, we'll spend a bit of time just kind of going through, giving you a bit of feedback. But yeah,
Yep.
without much further ado, we'll get stuck right in. Okay, cool. So, to begin with, what we're going to do is do some graph sketching. So I want you to sketch a couple of graphs for me. I'll draw a set of axes up here for you. So we'll have this as our y-axis. To begin with, I just want you to sketch the graph of y equals log base 2 of x for me. What would that
Okay.
look like?
Yep. Thank you for your question. From A level, I know that the domain of this function is that x, it's all the positive real numbers when x is 1, y is 0, and finally the limit as x goes to infinity of log base 2x also tends to infinity, so it's an increasing function. If I differentiate this, um, okay, I might have to use implicit, so y it's log 2x. That means 2 to the y is equal to x by the power rule of logs. Then I can implicitly differentiate both sides with respect to x. On the right hand side, this equals 1. For the left hand side, I can use chain rule to say this is dy dx multiplied by d dy of 2 to the y, which is 1. If I want to
Okay.
differentiate, yes, if I want to differentiate 2 to y, this will be log 2 multiplied by 2y is 1, so dy dx. That means dy dx, it's 1 over 2 to the y multiplied by log 2, if I'm not wrong.
Correct. Yeah, this is all good so far. This is what dy dx would be.
Yes, and then 2 to the y is equal to x. So this is 1 over x log 2, which is positive for all x, which is an increasing function. So I can go back to the graph and sketch it something like this. Intercept at 1, the limit as x tends to 0 is negative infinity. And it's a concave function with a second derivative that is negative.
Perfect. Yeah, absolutely. So it looks like this. So it's kind of has an asymptote on the y-axis, or the y-axis is an asymptote, passes through 1, 0, and has this kind of shape here. In fact, if you're able to change your pen color, that would be great. Maybe to red if possible.
Yep.
And can you now, on top of the same set of axes, sketch the graph of y equals log base 3 of x for me, please?
Okay, this is a bit interesting. So, let me think about the nature of this curve and how it
Mhm.
compares to log 2x. So, I can recall that log base a to the b, if it's equal to c, that implies a to the c equals b. Yes.
That's correct. Yeah.
So, if I consider log 2x1 and log 3x1, let's say such that x is greater than 1. For example, log 2 8 and log 3 8. I know that log 2x1 is going to be a little bit bigger than log 3 x1, right?
Why is that?
So, for example, if x1 is 8, then log 2 8 is 3, but log 3 8 is less than 2. And the reason is because the base is smaller. So A to the C, like that C would be a bigger for, if my base is smaller, the power needs to be bigger to get the same B. Yes.
Right. Yeah. I agree. Yeah, nice. So,
So
okay, cool. So we have this observation that log base 3 of a number will be smaller than log base 2 of the same number.
yes. However, I think in the range from 0 to 1, something different might happen.
Mhm.
So what I can consider is, again, I can consider something like log 2 of 1 over 8, which is going to be minus 3 because log to the minus 3 is 1 over 8. And then log 3 of 1 over 8 is approximately equal to minus 2. Yes, little
Yeah.
bit closer to 1, close, a little bit closer to 0. I noticed that the derivative of the second one, so log 3x with respect to x is going to be 1 over x log natural logarithm of 3. And this derivative, when x it's um greater than 1, would be a little bit smaller than the other one, but between 0 and 1 it's going to be larger. So that suggests the shape, like it might be a little bit steeper from 0 to 1, but a little bit shallower from 1 to infinity. But the
Right.
tendencies of this being increasing and being a concave function, because the second derivative is simply going to be minus 1 over x squared log 3, which is negative for all x. So if I want to sketch this, might look something like that.
Right. Oh, yes. Yeah. Something along those lines. I would agree. Yeah. And really well explained. Yeah. So of course it's slightly different to the log base 2 of x, for the reasons that you described. Okay. Cool. And obviously both of these graphs pass through this kind of this point 1, 0. Um. Now you might look at this and think, maybe these two graphs are the same, but rotations of one another. So if I take this red graph and I was to rotate it by some angle about this point 1, 0, you could maybe think just visually it could just so happen to coincide with the blue graph. Is that true? Is it true that if I rotate the red graph or equally rotate the blue graph around this point 1, 0, it will eventually coincide with the other graph?
Interesting question. My initial thought is maybe to consider some sort of like tangents at sort of like both curves at 1, 0 and try
Mhm.
to see the angle between the two tangent lines. That's one of my thoughts I'm having right now.
Okay.
Um, Seeing if this is like rotation, intuitively it would suggest that I'm rotating the log 2 curve a little bit like clockwise to like get it, and then I'm basically like sort of like pulling it th this way. Um I'm not sure if that is the correct way of thinking about it.
I like the idea. So you maybe can approach it with tangents as what you've done here and think about the angle in between. But then to think about how a graph rotates, there's no real super nice way of doing it. You can do it using matrices, but for this problem, that would be kind of overkill. Um, Maybe we want to consider the behavior. Obviously, these two graphs are different, but there is something about these graphs that they have in common. Obviously, the point 1, 0, but any rotation is not going to impact that. What other things or properties do these graphs have in common?
Maybe it is
Would
like
be useful to
properties of
consider.
log. So I know that the properties of log broadly sort of include log AB is equal to log A plus log B. This is true for both these curves.
Mhm.
Log A over B, it's log A minus log B. Log A to the B is like B log A. And I think the most importantly, I can like change the base of both of these curves with the change of base formula.
Okay, nice.
So maybe I can think about like log 3x in terms of base 2.
I
Um,
see, I see.
that would like give me a link between the two curves. So if I
I like
haven't
that approach, yeah.
forgotten my GCSE logs, log base A B, it's log C A over log C B, isn't it?
Almost, not quite. So the A and B would be the other
Oh,
way around.
okay,
So
okay, okay. So it
that's
is.
okay, no problem.
So it is. Okay, so it is B on the top.
B on the top and A on the bottom, yeah.
What I think C is any positive real number, right?
Well, technically, it can be
Greater
almost
than
any
one.
positive real number. It can't be one, yeah,
Yeah.
exactly.
Yep.
Um,
Okay. So then I can apply this by saying log 2 base x is equal to log 3. Um, okay. Now I see where it goes. X over log 3, 2. That means this is a stretch parallel to the y-axis with a scale factor 1 over log 3, 2, which I know is less than 1. And intuitively, this makes sense because if I go from the blue curve to the red curve, I'm like squishing it in the y. So it makes sense like the scale factor is less than 1. So I think it's not really a rotation, it's more like a transformation. It's like a stretch.
okay, that's an interesting idea. So I totally agree with what you've said that this is a stretch with this appropriate scale factor, 1 over log base 3 of 2. But why does that necessarily eliminate the possibility of this being a rotation? Why is it not possible that this could both be a rotation and a stretch? It just so, in this case, just so happens to be the same thing.
Um, with with a stretch. I'm changing the y value at any given x. With a rotation, I'm sort of changing the x value that that y value is achieved. So, like what I'm trying to say is that if f of x1 is equal to y1, then with a rotation, it could be the case that f of x2 is now equal to y1. But with a stretch, like if f of x1 is equal to y1, that would mean that f of x1 is now going to y2.
Okay, I see, I see. So it turns out that I can maybe see the logic here, but obviously one thing is mathematicians we like is a bit more maybe a concrete proof, but nothing wrong with getting a good idea of intuition.
Yeah, so
Annoyingly, what oh
sorry.
yeah, sorry, go ahead.
Yeah, I just was thinking that if I like differentiate the logs like generically, we
Mhm.
get like 1 over natural log of a over 1 over x.
Okay.
And like similar to exponentials, they have this nice property where there's like a one-to-one relationship between the x value and the derivative. So I'm thinking if this could be useful in the proof.
Hmm. Um, Potentially, I'd actually have to think about that. I'm not too sure. You've flipped the interview on me now, and I'd have to give that a think. But just to go back to this point up here, so um, annoyingly, what you said isn't quite true. So just because something is a stretch, that does not eliminate the possibility of it being a rotation at the same time. And to give you a very simple counterexample, if I maybe just draw my graph here, if I just take a very simple straight line, y equals x, and if I rotate that
Yes, yes.
some angle, yeah, hopefully you can see that that's now going to be the line y equals, I don't know, 1 over 3x or something, and it's obviously still it's just a
Right.
rotation.
Rotation,
So annoyingly, that argument doesn't work, but potentially there's something in there which means you can
yeah.
tweak it,
I'm
but not a
thinking
bad approach. I like that approach. We
I'm
may need to think about this another way though.
I'm thinking that like if I just take natural log of x and I take the line y equal to x,
Okay.
I know that this is the case where x is greater than natural log of x. And I know that like a Taylor approximation could be something like x plus 1. So,
For ln x.
yes.
Oh, okay.
So could I potentially use this by saying when I go from base 2 to base 3, like the first order approximation line changes and like it is like a rotation a little bit around that point?
So say that again. So you're looking at this curve and the tangent line for this is ln x, and you do
Yes.
this. Oh, sorry, not tangent line. You're approximating it with a linear function using a Taylor series.
Yes.
And your question is if you do that for log base 2 of x and log base 3 of x, then something happens.
Like
What was the
the yeah, like the approximation line has different equations. And it's similar to like the graph you've drawn before with like the stretch being equal to rotation with like a linear example. Could that be it?
um not quite, because again, this is only an approximation. So maybe in like a no local neighborhood of this point, it might be useful. Maybe there is actually something there. But maybe I'll give you a hint that this is much simpler, or the solution, or one way of proving whether these two curves are a rotation of each other or not, requires a very simple argument. So maybe I'll give you a bit of a hint. What we're going to do is consider this y-axis asymptote. So one thing that both these graphs have, log base 2 of x and log base 3 of x, is they both have the y-axis as an asymptote. So now we're going to focus on that property. How can we use that to help us think about whether they could be a rotation of each other or not?
Okay. When you say that, the answer doesn't immediately click, but maybe let me write it down so
Sure.
it might help me. So you're saying the limit is x tends to 0 the positive side, log base 2 or 3, x tends to negative infinity. So
Uh-huh.
the y-axis is an asymptote. Okay.
Correct. Yeah.
Um,
And the fact that that's also the same for log base 3 of x. So that exact sentence you've just written, if you swap the 2 for 3, it's also
yep,
true.
yes. Um, okay. So let me write it down for the other one. 3x, it's negative infinity, it's y-axis. Has it got something to do with the limit being the same?
Correct. Yeah. It's the fact that they both, well, more the fact that they both don't ever touch the y-axis. But if you think about what an asymptote is, it means it
Like,
gets
it's
arbitrarily
closer.
close.
Yeah, it gets closer and closer, but never crosses or touches it.
Correct.
So, but I'm not sure. I don't see how that will prove it's a rotation. Is it
So it
because like I'm rotating it by bringing it closer to the axis, but it still never touches it?
well, so it's actually to do with that. So these graphs are not rotation. So in fact, we're going to use the fact study something about the asymptote here. So something about the asymptotes tell us that these can't be rotations of one another. Um,
Okay.
what would happen if maybe we can try this via contradiction? What would
Yeah,
happen
yeah,
if these
yeah.
were
Yeah, yeah, yeah.
rotations?
Yeah. It would just be if I take x in the limit at 0, if they were rotations,
Mhm.
then the log 3 one would cross the axis. I think that is clear intuitively, right? Because that is why I was a bit stumped because in my head I think they can't be rotations, but I thought I was trying to prove they were. So if I take the log 2 like this,
Uh-huh.
we know that the limit as x gets arbitrarily close to 0 is negative infinity. If they were
Right.
rotations, that would suggest that I get something like this. Um, and therefore there must exist like some point here. Let me label it x1, where log 2 of x1 is negative, but log 3 of x1 is 0, because that is what like a rotation kind of does. Like that's what I try to say with like the f of x1 is y1 or f of x2 is y1.
I
Um,
see, I see.
and then this obviously is a contradiction because we know that there doesn't exist any x in the range 0 to infinity such that log of that could be 0. So they can't be rotations.
Right, yeah, exactly. I mean, yeah, we can kind of see if we did rotate this, this would have to hit the y-axis, and we know that any log base some number x can't ever hit the y-axis. So yeah, so these graphs are actually not rotations of one another. I think this is kind of a cool problem because the answer is not super difficult to understand, but not maybe very obvious of how you'd come up with it. So there's lots of different approaches to be explored here. So we talked about derivatives. We thought about stretching and things like that. So it's a nice little problem to explore. Um, awesome, cool. We'll move on to the next problem.
Yep.
So what I'll do is I'll just draw a big line or something. That box perfectly, yeah. And we will have a look at another problem. So this one's going to be a bit more focused on integration. So we're going to look at some
Okay.
integrals. So hopefully you did some integration as part of your time doing economics. Might give you
Yep.
some flashbacks. So just going to start very simple for problem. Simple to state at least. I want you to just integrate a function for me.
Yep.
Can you please integrate the function sine x times cos x for me, please? Dx.
Yes.
An
What are the limits,
indefinite
or is it
integral.
like an indefinite
Just an indefinite integral for now, yeah.
okay. Um okay. I can let this label I. I can notice that sine 2x is 2 sine x cosine x by the double angle formula I learned at A level. So I is going to be a half integral. of sine 2x dx,
Yep.
then I can do like a new substitution for u for 2x, make it a bit more rigorous. So du dx it's 2. That would imply it's a half of sine u um dx. It's du over 2, right?
Correct. Yeah.
That would imply this integral is I won't forget the plus c, don't worry. Um
That's fine.
I think minus 1 over 4 cosine of u plus c. U was 2x. That implies the integral of sine x cosine x. It's minus 1 over 4 cosine 2x plus c, where c is some constant of integration. Is that correct?
Nice. Yeah. Absolutely. Maybe just
Okay.
don't forget your
Good.
DX, but don't worry about that.
Okay.
Um, nice. Very nicely done. Okay, cool. So we're gonna now give you another integral, and we're gonna build on
Yep.
this. So next one I'm gonna give you is the integral of sine x times cos squared x dx. So quite similar, but slightly
Yep.
different. Obviously, this one's cos squared x dx, and again, it's an indefinite integral.
Okay.
How could we go about integrating this?
Okay. Okay. Let me label this J. My first thought is to replace cosine squared x with 1 minus sine squared x, but I think that may complicate factors a little bit because then I'm introducing sine cubed into the integral.
I
My
see. Yeah.
second thought is to do it by parts. Um, that may work, but it may make it more complicated. I'm thinking of maybe a substitution I could do that could be relatively smart to cancel a few factors. So I know that cosine differentiates to sine. So maybe let v equal cosine x. That means dv it's minus sine x dx, right?
Correct.
So j is the integral of sine x multiplied by v squared over dv minus sine x. I think um I can cancel out the signs if I have the condition that sine x can't be zero.
Correct. Yeah. So here we're assuming this integral. We're not worrying about any of those issues, but it's good to consider those.
Yep.
So when we're dealing with an indefinite integral here, we're just going to assume it's over some nice
Yep.
enough interval, which is yeah, no
Yep.
divided by zero.
Yep. Then I use the power rule. So I add 1 to the power 3 divided by the new power. So minus 1 over 3 b cubed plus k, where k is a different constant of integration. V was cos of x. That means the integral of sine x cosine squared x dx. It's minus 1 over 3 cosine cubed x plus k. I may spot a pattern by maybe generalizing this integral to like sine x multiplied by cos to the n power x, where n is a natural number. Because
What would the value for that integral be? What would that equal?
um actually like the method will be exactly the same because I could just substitute and get rid of the signs. So if I generalize this result to sine x cosine n x dx such that n is some sort of natural integer. If I
Yeah.
do a substitution of like v is equal to cosine, that the sign cancels from the derivative of that, I would get then v to the n minus v to the n. The integral would be minus 1 over um, n plus 1 times by v to the power of n plus 1. That is very similar to the result, which we got before, which is just minus 1 over n plus 1 cosine n plus 1 x plus c.
Perfect. Very nice. Yeah, so you're absolutely right. This does generalize quite nicely. And it's a great observation there. So we kind of see the pattern. There was nothing really special about having the number two here. You can replace it with whatever positive integer you want. It might be interesting to explore what happens if n is not necessarily a positive integer, but we won't do that now. But that's something maybe you can have a think about. Okay, really nicely done. Again, I'm just gonna kind of give you another integral, and we're gonna build into more and more complicated integrals.
Okay.
So the next one is gonna be the integral, oops, sorry, sine cubed x. So you can maybe guess the theme for these integrals times cos to the 4x dx. So they're all similar to before, indefinite over a nice interval. We don't have to worry about any division by zero.
Okay.
How would we approach this integral?
Um, my first thought comes to substitution because I think the cosine 4, if I do chain rule, is gonna like cancel with the sine 3. So let me try that.
Okay,
Um, so I can let this equal to, let's say, I1. So um I can let u equal to cosine to the fourth x. Du dx by chain rule is, first I bring the 4 down. I differentiate cosine by itself to get minus sine x. And then I have this to the um wait, sorry, let me try again. I'm gonna confuse myself.
that's okay. Take your time.
Yes, so let me do another substitution. So let v equal cosine x. So dv dx, it's minus sine x. Du dv, it's 4v to the cubed. Combining this by chain rule, which is du dx is going to be dv dx multiplied by du dv. This would be minus 4 sine x cosine cubed. Okay, so I was correct. Um, okay. Okay, this may simplify a little bit. So the integral becomes minus the integral from sine cubed x cosine fourth, and then du dx is that. So dx, it's du over minus 4 sine x cosine cubed, right?
Correct. Yep, absolutely. Doing the substitution.
Then we would get 1 over 4. Wait, the minus I already took out. So, okay, then we would get minus 1 over 4, the integral of sine squared x cosine x du. Yes,
Sure. Correct. Yep, absolutely. Nice.
where u is cosine 4 to the x.
I think you was just oh yes, you was cos to the 4x. Yeah.
Yeah.
So it feels like well, I mean, you've got to an integral here, but I'm not sure how you would get this bit here in terms of u nicely. I mean, this bit would be like u to the quarter. Well, maybe you can do this relatively nicely.
Yeah, because
Um,
cosine to the fourth x, it's cosine squared x squared, which is 1 minus sine x the squared.
Yeah.
Um, so u to the half, it's 1 minus sine squared x. Sine squared x, it's 1 minus u to the half. And then the cosine x is just u, or I had u, yeah, u to the quarter. So the integral becomes the integral of um 1 minus u to the half u to the quarter du, yes,
Yeah.
which is u to the quarter minus u um 0.25, so 3 over 4
Right. Yeah.
du. This is add 1 to the power 5 over 4 divided by the new power, so 4 over 5 u 5 over 4 minus um add 1 to this power to get 4 over 7 u 7 over 4 plus c. And
Brilliant.
then
Yeah.
I can replace this with 4 over 5 cosine to the fifth x minus 4 over 7 cosine seventh to the x plus c.
Yeah, really nice. Yeah, exactly. Nice. This is exactly one of the ways that we can solve this. So the crucial thing is we did a substitution here to get to our answer. Okay, and so you can see I've given you maybe three or so integrals so far, and they've all been kind of this form, like the integral of sine to the mx times cosine to the nx. And in all of the examples we've looked at, m and n have been just various fixed positive integers.
Yeah.
The question I now have is, well, if I gave you m and n, but m and
Mm,
n now could be very big integers. Obviously, we've looked at quite small cases.
mm,
I'm not necessarily asking you to integrate this, but I'm
mm.
asking you, how would you know if you could integrate this? So if I gave you some value of m, some value of n, let's just for argument's sake, for example's sake, say m is 10 and n is 13. How would I know that I can integrate this
So you're saying
using like one of
asking
the
if the integral exists.
essentially, well, I mean, so not if the integral exists, but if we can kind of find it using a technique like substitution. So using
Okay.
mimicking it like the techniques we've used up here in the previous
Is
integrals.
it something to do with the size of n and m? So if n is greater than m, it exists. Because in the previous example, n was greater than m and it existed. And the reason it existed was because I could cancel out some of the cosines and get the relationship between sine and cosine from the squared form. So that's my first idea. Um, we've looked at in the start what happens when um m is fixed to 1, n can be free. That always happens, right?
Nice, yeah, yeah,
So
nice. So when m is
m1,
fixed,
this is free, this exists. Um, maybe the same thing would happen if n is 1 and m is free. Would that work? Um, maybe I can try it, but
yeah. So so you're saying if just at n, so the power of pos is one. Is that what you're
yes,
saying?
yes,
Okay, yeah. So if I just for the sake of time, I'll save you working out. The answer is yes, you can. You can,
okay,
and using a very similar argument. The
yes,
crucial factor in that argument, in fact, is that sine and cos, for the sake of this, are virtually the same thing, in that one differentiates to the other. It's just sometimes you get a minus symbol chucked in there, but that doesn't really affect the difficulty of the integral.
yep.
But what about when m and n are bigger than one? Like, so we did one just here where we had a three and a four.
Hmm.
Was there any what exactly about the three and the four made it so that we could integrate it, or was there nothing special about three or four? Would it still work
Maybe
if
the
three or
mod
four?
of m minus n equal to 1. Um,
Okay.
maybe it could be the case that when n is greater than m, it works. Um,
Interesting, interesting.
maybe,
Um, yeah, go ahead, sorry.
yeah, those are the two patterns I spot. Yeah,
Okay, cool. So it's actually what we need here, and it's maybe not so obvious from your the substitution you did, but what we need here is one of these numbers, either m or n, or both of them, doesn't matter. We need one of them to be odd.
odd.
So, and just well, we've kind of hit the time here, so just for more to appease your mathematical intrigue, I'll briefly explain why. So, if m is odd, let's say, and as I say, it doesn't really matter. M and n are essentially the same. Cos and sine are essentially the same thing. For the sake of this integral, it's just the arguments are going to be very similar. Let's say if m is odd, so we've got the integral of sine to the mx cos to the nx, and we're assuming that m is odd.
Oh, sorry, could it be like I can split sine by saying sine x multiplied by sine to the 2k, where k is some.
Yeah, you're absolutely right. So if you're at m is 2k plus 1 for some integer k, this would become integral of sine x times sine to the 2kx times
And
cos to the nx
yeah,
dx.
and
And
then the
why
sine
is thinking of it
can
like
be
this useful?
because I can represent sine 2k as a function of cosine. And then I can differ
Exactly.
I can do a substitution to cancel sine, basically, because
Yeah,
they're
what would your
different
substitution be here?
cosine, because
Yeah,
I could get 1 minus cos squared to the power of k, and then use a substitution of just u is equal to cosine, get rid of sine through the substitution, and just differentiate this easily using the power rule.
nice. Yeah, absolutely right. Yeah, so that's what happens if m is odd, and it's very similar when n is odd as well. So that would be the how we do this. And in fact, you can integrate this if m and n are both even as well, but that's maybe a slightly different technique. So I encourage you to explore that. But we'll finish there, so you can maybe breathe a big sigh
Sure.
of relief. How did you find that?
It was good. I haven't done much pure math type of stuff. It was interesting. It kept me on my toes, and it was fun as well.
Nice. That's good to hear. Good to hear. So you'll actually be, or maybe find this interesting. This second problem here about integrals was actually given to me as one of my interview questions
Wow.
back in 20, goodness, I'm showing my age here, 2017. So quite a while back. But yeah, this is one of my interview questions.
And did you
So
get it
in fact, this
correct?
one, say that again, sorry.
Did you get it correct?
Yes, well, so here's as I'm sure you know, with interview questions, they always have like layers to them, especially the maths one. So this is as far as I got with the problem. Maybe there were more layers to it, or maybe it could have ended in various ways. But I got to this idea of M and N being one of them had to be odd in order for this technique to work. And in fact, this interview was quite interesting. So this was back in the day where interviews were in person. So sadly, they're now all online, which I think is not a great thing. I think it's it would be great for students to come and visit either Oxford or Cambridge and have their interviews here. But anyway, that's besides the point. But this interview, interestingly, was in person, and they actually got me to do this on a whiteboard. So the two interviewers sitting at a desk, and I was physically writing on a whiteboard explaining my workings. So I don't know. I quite enjoyed that one. It's quite memorable. And yeah, the first one wasn't one that I was given in an interview, but the second one was. Okay, cool. So what we'll do now is I'll kind of just go from the first question again. We'll briefly discuss the parts of the problem, but also like the things I've made notes on, what I thought went well, what things could be improved on. And if at any point you have any questions, just shout out. I'm just going to scroll back up here, back to the top. So the first problem was to do with the logs and essentially whether the graphs are rotations of one another. So to begin with, I got you to sketch the graph of y equals log base 2 of x. And what I really liked is that you didn't just sketch it, because I'm sure anyone who's applying for maths or math subject can sketch graphs pretty well. That's kind of drilled into you in the A level course. So you didn't just sketch it and say, right, what's the next question? You explained your thought process. So you said, okay, I know the domain is this. I know that it's going to pass through 1, 0. I know that the limits are this and this, and you maybe potentially gave it went into a bit too much depth. You started talking about the derivative, which I didn't think was super necessary, at least at this stage. Potentially could have been necessary depending on what the problem was. But at the stage where it's just a graph sketching problem, yeah. But nonetheless, it's never too bad to give too much detail in the real interview. If they think you're spending too much time, they'll just cut you off. But it was good to know that you were happy with all of that and you explained your thought process, which was good. And oh yeah, one thing, and you kind of did this throughout the interview, and this is a skill that's kind of maybe more for the modern interviews where it's all on a Zoom on a whiteboard, a virtual whiteboard, is getting you're very good at talking and explaining your thought process whilst writing or whilst drawing, which I think is very important. Purely from a time point of view, the interviews are obviously, fixed length in terms of time, and you don't want to be spending time explaining something and then visually explaining that again by writing or drawing it up again. So it was really good that you had that skill of being able to do both of those things. Um, yeah, I guess I'll maybe pause and let you have. Do you have any comments on that or anything from the problem so far?
Yeah, I do agree. I think differentiating felt like just forced. It wasn't really necessary. Maybe I could have just said the first derivative is positive and it's concave rather than deriving it.
Mhm.
Um, but I think, yeah, while speaking and doing maths, it's like a lot of practice is needed. So it's important that you
Absolutely, yeah.
practice the skill before your real interview. Because in the real interview, it's unlikely you can do it for the first time randomly unless you practiced it before.
Of
And
course, I 100% agree. Yeah.
yeah, so I think that is a good thing you guys can practice.
Yeah, absolutely. So yeah, getting used to writing and talking, and it's also just talking about maths in general. Is in school, you're never really taught to do that. You're always, assessed via exams where your head down and you're forced to be in silence. So it is good to practice talking to maths, talking about maths. Sorry. Um, Nice, yeah. Then you also sketched y equals log base 3x, and I like that you didn't go through all the faff of doing all this derivative stuff again. With three, you just said, okay, well, the derivative is this. It's pretty self-explanatory that the argument's going to be the same. Um, cool. What else have I got here? So we went through this problem. You stated your log rules, and then it was interesting your approach here. So I didn't interrupt you. So you talked about maybe it's a scale factor. So I thought that was a really interesting approach. And one thing in the interviews, then they're not going to penalize you for not having the right answer. It's more just a way of seeing how you think. So it's really interesting that you had this thought and you kind of progressed along with it. And a lot of the times also, and I'll mention this with the second problem as well, you kind of use the phrase "a thought I have is," or something along those lines, where you are saying I have this idea for how to solve the problem. I don't know if it's going to be the correct idea or not, but it's just an idea. You're kind of putting it on the table. And then you had a few ideas. Um, and then you kind of assess, okay, which one will be the best one. Um, but yeah, this problem is a nice little problem. They're not rotations of each other. Maybe it would be nice, like at this stage, if maybe you could give a counter example, but obviously it's not if you think so here I gave you the counter example of why something can be both a stretch and a rotation in at the same time. So it would be nice to, but obviously I guess yeah you were thinking it wasn't true. But yeah, that nice little counter example there for you. But there's also yeah you had this other idea of the Taylor series approximation. But yeah, we got to the answer in the end, which was good. By thinking about this asymptote and the fact that one of them would have to be the rotation, couldn't be the rotation of the other, otherwise it would have to hit the y-axis, which is impossible. So yeah, really nicely done. Now, I can't remember where I've heard this problem before, but I thought it was really interesting, and it's almost like a really nice interview problem because yeah, it's not something most people would have seen before, or thought about, but it's a quite a cute little problem.
Yeah, I've never actually seen this before. It was like first time for me as well. Quite interesting.
Ah, nice. Yeah, and if I mean, maybe if you're curious, or any viewers are home curious, have a think about like why exactly you can or how you can rotate a graph. So it's probably easiest to think about the origin, and if you've studied maybe 2D matrices and rotation matrices, what's very interesting is how you can take the graph, f of xy equals equals 0, and then transform that into rotate by theta, anti-clockwise around the origin, and this turns into g of xy equals 0, and think about the relationship between f and g. And so this can all be studied. It's not too overboard. It's not too difficult to work out what the relationship between f and g is if you have studied matrices before.
Is this
But that's
like
a
a
nice little
Jacobian matrix?
um potentially. So now you're I'm trying to recall what a Jacobian matrix is.
Because
But
we did
I
it in
think it is
stat.
something to do with it.
Yeah,
It's
like
like
we
when you
did
have like
it.
cos theta minus sine
Yeah,
theta, cos theta.
yeah.
Yes, essentially that. You will have to so essentially if you take, let me give you an example. If you have x squared plus 3xy minus 5 equals 0, that's your original curve. So it's a very weird curve. Doesn't necessarily have to be a function. You don't like if I make this very horrible and put like something like this, something where it's very difficult to make y the subject. If I now replace, so let me just make sure I'm getting this right. Um, so this is the rotation matrix cos minus sine sine cos. If you expand this, you get cos x minus sine y, sine x plus cos y. From memory, if you replace all the x's in this original equation with cos x minus sine y, and replace all the y's in this equation with sine x plus cos y, and you'll get some new equation that will be your g. Um, so just replacing all the x's with these things in terms of cos and sine. Um, but yeah, any kind of thought of doing that in this problem would almost immediately be shut down by the interviewer because it's overkill. I mean, maybe it might get you an answer, but it's not going to get you an answer quickly. Um, but yeah, apart from that, in general, really, really good. I was really impressed with problem one. Again, one of the main things is they're not necessarily looking for you to get the answer. That's not the point of the interview. The point of the interview is to assess how does the student think on the spot? How do they take the tools that they've learned in school, these mathematical skills, and how can they apply them in unfamiliar scenarios? So I thought you did that very well. You had different approaches to the problem. Let's move on to the second problem. So this integral or various integrals we built up to. Um, so yeah, what have I got here? Oh yeah, a very small thing, but I liked it is labeling, giving the integral a name, so you don't have to keep writing the integral down a million times. It's a nice little trick. Well, not even a trick, even, but just a thing that you
Notation.
should definitely try and do.
Yeah.
I've seen lots of students either rewrite the integral or they'd like use lots of arrows and it gets very messy. So just give it a name. So that was good to see. Um, um, and then, oh, sorry, this first integral, pretty straightforward. You knew exactly how to do it straight away. There wasn't really too much discussion. You said, okay, well, I knew that I can use this double angle formula. That gets quite nice. And then we got to this second integral, J, and it was the integral of sine x cos squared x. And what I really liked, and I mentioned this with the first problem, is you explained various ways that you could go about it. You initially said, well, my first thought is to replace cos squared with 1 minus sine squared. And then you went, maybe not, because then that would introduce sine cubed. Then you said, okay, well, maybe I can do this by parts, maybe not. And then you said something like, I can't, you said, oh, maybe you can do this by parts, but I'm not sure how easy or hard that would be. And then you must have realized, oh, actually, this is just a nice little substitution. But you walked me through your thought process, which is really important. The one tip I always give with interviews is think out loud. And I think throughout the interview, you did that very well. So yeah, you said cos squared x is 1 minus sine squared x. And then you kind of went ahead and evaluated the integral, nice and straightforward. And then what I quite liked is you then actually went, hold on a minute, I think there's a nice generalization here. It generalizes quite cool, quite nicely to sine x cos to the nx dx.
I think this will be
Also, you can
minus.
integrate this.
Yeah.
Yeah, and I think you did. I'm not sure what happens to the minus, but there should be a minus there.
Yeah,
I'm pretty
minus.
sure you did say that. But
Yeah,
yeah,
maybe like, yeah, zoom. I don't know. Yeah.
no worries, no worries. But yeah, so if you do spot a pattern and it's something that's quite quick to just explain, I'd say definitely do drop it because that's one thing that makes you stand out as a mathematician is the fact that you can spot patterns. Even if you're not applying to study maths, that's a super useful skill is being able to spot patterns. I think that applies, I'm sure you had that in economics where in maybe your problem sets or something, you had to kind of spot something that
Yeah.
was
And
similar from in lectures.
yeah. And also in some problems when the problem is very difficult, if you
Mhm.
simplify it, spot a pattern, then you can extend that pattern to like the actual problem. So that is also useful in that sense.
Absolutely. Yeah, we do that a lot in maths. In fact, lots of proof by induction is kind of that, where do play around with it with small values of n, and you go, hold on a second, there's this nice pattern going on. And then you can go, maybe this pattern holds in general, and then you prove it by induction. Um, cool. And then this last, or not last integral, the I1 integral, the integral of sine cubed x cos to the 4x. Um, so this one, I mean, you use the substitution that actually worked out in the end. It wasn't the substitution I actually had in mind. The substitution I did have in mind was u equals cos x. But again, you realize substitution can kind of work here. You went through it, and there was a good bit part here where you weren't sure if you'd done the derivative correctly, so you wrote out the chain rule in full. That's pretty good. Um, yeah, and evaluated the integral, got to the answer in the end. Great. And then we had this discussion about if we replace, you do sine to the mx and cos to the nx dx. When will we know if we can integrate this? And you said, well, we already know if m is if one is one and n is any number, it works. And we said that if n is one and m is any number, it works. And you can actually check that. It's because sine and cos are essentially the same here. And then we were well thinking about other examples, and you said maybe when m and n are one apart, or if n is bigger than m. With this particular one, I guess you can kind of know that it won't. Well,
It's a
the answer kind
contradiction
of
if you
won't do
point
this.
to, yeah. It's like, it's,
Kind of. It's the fact that M and N here are essentially they have the same role, right? It
yeah,
just one is because sine is the same has the same effect as cos in this, except you might have a minus sign. So if it was n is bigger than m, it would also have to be m is less than n. M is bigger than n, sorry, which would then
yeah,
mean basically all pairs
yeah. Also,
potentially.
if n is greater than m, then n being equal to 1 and m being 3 cannot work, but we know that works. So this is wrong, yeah.
Yeah. But yeah, it's also not suggesting that these are the only values. So here I've said if one of them is odd, is what we concluded. It actually also you can also integrate this if both m and n are even. You can just easily integrate sine squared cos squared x. Um, but this technique you can generalize to if m is odd or n is odd. Um, but yeah, I think that was done really well. One very small thing, which I think I liked, and it's worth mentioning to the viewers at home. It's actually with the first problem I just remembered was you with the logs, you were kind of writing your log rules. I'm just trying to find where here.
Yeah, up,
And I
yeah.
think it was this change of base rule that you kind of maybe slightly misremembered, but you asked, you said, have I got that right? And I corrected you. You know, it's in interviews, it's not a big deal if you can't memorize a formula. That maths and also any subject that requires maths is not about memorizing a formula. If you can't remember a formula, it's not the end of the world. In the real world, annoyingly, A level teaches you it is the end of the world if you can't memorize a formula, but I promise you it's not. So if you can't remember one in interviews, yeah, you just ask the interviewer, or they'll probably point it out if you've got it wrong. But if you're not sure, maybe just say, "Sorry, have I got this one correct?" So that was good. Awesome. I'll stop rambling on. I think that was done very well in general. Do you have any thoughts or comments, Deb, from your side as the person sitting the interview there?
No, I think you gave like a pretty good approximation of what to expect. My interview, even at the mathematical part and the economics were quite similar in how they build up in difficulty.
Mhm.
And the interviewer isn't really out there to trick you. So like how you were genuinely helpful, you didn't try to like trap me by like not providing hints. Like that's a myth that some students believe, but in real life, professors are very willing to help. Um, maybe I think I could have been. Maybe do you think I should have taken more time to think, or like was I too quick with my um like answers, or was it okay?
I think not in general, it was okay. I think when you had ideas and you said, okay, here's this idea, here's this other idea, you know, and you kind of said, here are some ideas I have. Maybe at the start, like when you were sketching the log base 2x, you kind of straight away said, you haven't sketched anything, and you said dy dx is this, um, which you didn't
So
really need in the end. But I think, you know, those things happen. I think in general, it was a good level of, you know,
speed and
not talking to, yeah.
accuracy. For like these easy graphs, would you recommend students first sketch the graph and then provide the additional information, or provide the information first, then sketch it? Because if the
Um,
graph is very difficult, then you have to give the information first. But if it's like an easy graph, do you think like the reverse could work?
I don't think. Well, if it's like, for example, the graph, like let's just to play just to really make it clear, if they gave you a straightforward graph, y equals x, I mean, you would just draw a
Yeah,
straight
yeah,
like a diagonal at 45
yeah.
degrees. If it's something like this one, log base 2 of x, which maybe you know what log ln of x looks like, but it's log base 2x, the same thing. Just a brief explanation. I don't think there's ever like a strict you have to say exactly this amount of words or whatever. But yeah, obviously, the more complicated the graph becomes, generally, the more you would say about it before kind of sketching it. I like to sometimes think of it as a game of connect the dots, where I will start by they'll give me a graph and I'll say, okay, cool. If it's a graph which is a bit weird, I might say, okay, my first thought is maybe let me think about where the intercepts are. Okay, the y-intercept is 3 and the x-intercepts are 2 and 5. Okay, let me just mark those on. And then I go, okay, well, this looks like it maybe is a polynomial. So maybe I'll think about the behavior as x goes to infinity and minus infinity. Okay, it starts at the bottom left, ends in the top right. Maybe this has some turning points. Are those nice turning points? Okay, yeah, it has turning point here, here. And then once I've kind of considered all the main parts of the graph, I can kind of put it together. So explaining, but also slowly adding to my picture. But it is a bit of an art, like in the sense that knowing how much detail to give. Obviously, you don't want to spend too much time going into too much depth because then you don't have enough time to get into the meat of the question. But normally, the first questions in the interview are certainly just there to warm you up, get you a bit comfortable talking and writing as well.
Cool.
If you are interested, go and follow Dev. He's on TikTok and YouTube. So I'll link all of that in the description below. But apart from that, thank you so much. And hopefully I will do a reverse video on his channel and maybe a bit more economicsy math. So I've not done economics before, but hopefully it'll be a nice fun challenge.
Thank you so much.
Awesome. Take care and have a great day.